So now we have the pleasure to welcome Emmanuel Cande. He's a professor at Stanford University. He's very known for his contribution to mathematics, statistics, and I think he's also professor of electrical engineering by courtesy. He's doing a lot of things. Recently, over the last few years, he's made some very nice contributions to conformal prediction, among other things. And I thought that would be very nice to invite him to come today, share his thoughts on AI and statistics. And I'm sure he's also going to talk about a lot of other things. So, Emmanuel, the floor is yours.
Thank you so much. Thank you so much, Pierre, for the very kind introduction, and thank you for coming so early. I really appreciate that. And before I get started, I just want to know that I really like the title of your conference. I think to call this a symposium on forecasting is really a great name. So congratulations for that. And as a result, what I've tried to do is I try to kind of tell you about forecasts. I'll try to stick to the theme of the conference. Okay, so I'm going to basically talk a lot about AI today and how we can calibrate it with confidence. So AI is very happy to make forecasts, and how do we calibrate these forecasts to have anything meaningful? And then if I have time in the end, I want to tell you a little bit about what we've been doing in our lab on frontier LLM questions. I've been involved in pre-training, which is a bit strange, but if I have the time, I'd love to tell you a little bit about that. So I want to start with an important forecast problem. We're going to talk a lot about forecast problems and how we can calibrate AI systems so that we can basically use these forecasts reliably. And so we're going to see 2 or 3 vignettes of these types of problems. And I'm going to spend most time on the first vignette, which has to do with drug discovery. So we live in an exciting time. So this is a library that DeepMind has released. So Google DeepMind has nearly 400,000 new compounds. So DeepMind has given us 400,000, in fact more, compounds. These are like molecules or proteins that you could possibly synthesize but that do not exist in the wild. And so people would like to examine and sift through this huge library to understand which compound would be effective for a certain target. So we're going to talk about drug discovery. We want to find a new drug for a target disease. And so I don't think I need to tell you that, drug discovery is an expensive proposition. It costs a lot of money to bring a new drug to market. It takes a lot of time. And so against this background, there was this idea that, AI will speed up the time and reduce costs. So why is that so? The reason the drug discovery pipeline is very slow and time-consuming is that it goes something as follows. So you have a disease that you care about. This is this guy. And you have candidate drugs. And so you have a lot of candidate drugs. And so what you would like to know is which drug will be effective for that disease. Chemically, that means like if you put this drug, would it bind at a specific site on the target disease? And so to do this, we need to kind of make physical experiments. And so we're going to evaluate an activity score. An activity score is an affinity of a drug, a compound for a target molecule. And then we're going to try to screen thousands of these guys and then shortlist a few. And then if these few shortlisted candidates are promising, we're going to go to clinical trials and hopefully get FDA approval. But because we have to screen a lot of stuff, this process is very, very expensive. So the idea of AI and what people do is says, well, now that we have AlphaFold and tools like this, wouldn't it be cool to replace the expensive physical screening with a virtual screening? Is it not possible to predict the affinity of a drug for a target using AI? But of course, AI is not perfect, especially in our world where, and you'll see a lot of real results on real prospective studies in a minute, it's not perfect, especially on drugs that do not like anything like AlphaFold has ever seen. So, so we're going to have this problem where we are starting with a molecule. Maybe we want to use a very, very fancy neural network or graph neural network, and we use extraordinarily complicated stuff to make affinity predictions. And so we hope that by doing so, we're going to reduce cost and time. But if you look at it, if you look at Nature and papers and editorial opinions, AI potential to accelerate drug discovery needs a reality check. It's not going as well as we'd like it to be. Okay, so we need to be a bit careful, because if AI makes a lot of mistakes and I send the mistakes to the lab, I'm going to waste a lot of resources doing things that are not of value. All right, so we're going to talk about this, which is how can we use AI to make discoveries with few mistakes. So the problem is extremely simply stated. We have a list of drugs. This may never have been synthesized before, and we want to know which ones are active. Okay, so that's the question. A very, very simple question. And if I were to couch it in terms that you might be familiar with, it would be something like this. So we have features, and for us, the features in this problem might be the amino acids of the drug, the sequence of amino acids, other chemical features of the drug, etc., etc. These are the features. This is what you give me. And what I want to know is that the affinity of this drug for target. All right? So this affinity might be binary, whether it binds or not, or it might be how likely it is to bind, or things like that. Okay, so we have some features, X, and we want to predict Y, which is the affinity of my drug for my target. And so what is a problem that really people care about is I got some training data, not a whole lot, because we were not able to make a lot of physical experiments, because recall that these are very expensive. So I have some data where you gave me both the physical, the sequence of amino acids and the binding affinity. These are the screen drug, and maybe this uses AlphaFold and very complicated stuff under the hood. And then I have a library of test drugs that I would like to scan. And so these are my test samples. So in this presentation, training is in blue and testing is in red. And I have my test samples. And of course, I do not know their affinity. All right, that's what I want to know. So I just get to see the chemical structure, and I want to know whether it will bind or how well it will bind. And so I don't know the Y's for those. And the problem that we're going to have to solve, you and I, are to find from the X alone those molecules for which their Y is above a threshold. So the lab will say, there's a threshold that makes a drug interesting. The affinity has to be higher than something. And that number might be random. It might be, for this class of drugs, it has to be at least as good as 95% of the stuff I already know. Right? So it might be random. And so basically a lab will set a threshold, and they want to know ahead of time. So you see, it's a kind of a very beautiful forecasting problem. They want to know ahead of time which of these will exceed this threshold, which of these will be interesting and I should pursue. And that's a forecasting problem which is very different from the kind of forecasting problem I studied when I was a grad student, because we're very, very far from parametric models here. Okay, so this is a forecasting problem. Which of these drugs will exceed a threshold that I determine? That might be different for different class of drugs. Okay. So this is my forecast. So you see, I try to make an effort in trying to make my talk relevant for this audience. And it's actually what you'll see at the end. We work with Genentech a lot on this stuff, and that's what they ask us. And they'll say, Emmanuel, my AI model told me to synthesize the 30 new drugs. How many will be potent? Or they'll say, I want to find at least 30 effective drugs which are sufficiently different from the drugs I already have. How many should I synthesize in the lab to get 30 hits? How many drugs should I synthesize before I make 34 mistakes? Maybe you have a budget that you can waste, but you cannot waste more than 34 experiments. And the question we're going to study, we can give answers to all of these questions, but the question we're going to study is the one that I circled in red, which is, how many drugs can I synthesize until I make 20% mistakes? That is, you're a lab director and you're willing to waste resources, but you want to control the fraction of wasted resources and time. So you might say, I don't want to be the director of a lab where 90% of the experiments end up in failure. So you set a threshold, maybe it's 20%, maybe it's 50%, and you say, Emmanuel, I'm willing to do as much testing as possible, but I don't want to waste more than 50% of my time. Okay, that's a goal. And so we've written a series of papers going from quite theoretical to very, very concrete, since I'll show you new antibiotics that we found that addresses all these questions. So I'm going to say that this is a tough problem. And why is it a tough problem? Because the AI system is very willing to kind of give you predicted affinities, but if I want to control the number of mistakes that I make, then I need a sense of reliability of these AI predictions. Of course, there's no parametric model anywhere in sight, and we're going to need to deal with an enormous problem, which is a problem of distribution shift that I don't know if you guys talk about, but this is an enormous problem in this field, for reasons that you might suspect. So, in drug discovery, it's the case that the data for which I have the labels and the data for which I do not have the labels, these top populations are different. And one of the reasons is that I have labels for some molecules because they looked interesting in the first place. These test drugs, they don't even exist in the wild. They are quite different from the data for which I have labels. So it's a bit like, these tools that we're going to develop can be applied to many, many other settings. For example, how you screen candidates. So you have features of a candidate, you want to do whether they'll be good at their job. That's a similar problem. And you don't want to hire too many people who will not be good at their job. That's your forecasting problem. But the problem is you only have data for people you hired. And the people you hired look different from the people who apply. And so here it's the same thing. Except that here we have something that works for us, which is that if there's a distribution shift between the training and the testing population, it's only at the level of covariance. That is, if I were to be fancy for a second, the likelihood ratio between the test distribution and the training distribution is a function of X only. Because affinity depends on X, it's physics. That doesn't change. A molecule will fold in a certain way and will bind or not, doesn't care whether you're in a training or test set. That's physics. That doesn't change. But the distribution of molecules, the sequence of amino acids might change between test and training set. So we have an interesting problem in which we have, if we have a shift, it's a shift in X but not in Y. Okay. So I have my AI system, and we use systems with hundreds of millions of parameters, and they make a prediction. And so I need to quantify the reliability of this prediction. Now, there's a field of research named conformal prediction that is able to turn essentially a point prediction into a prediction interval or predicted range with valid coverage in the following sense. That is, it's a methodology that was largely developed by Vladimir Vogt and his colleagues, and maybe people are familiar with conformal prediction. Pierre, they are? Okay, that's fantastic. So you know about that. So can I skip that? You know that you can get a prediction, and it's model-free, and so. Can you raise your hand if you've heard about conformal prediction before? Okay, a lot of people. Okay, so that's wonderful. For those who have not heard about conformal prediction, it's a method that basically takes a point estimate and returns a range of values with prescribed probability of coverage, but coverage not in a sense that you cover the parameters. There's no parameter in this world. There's just random outcomes. And so what it means to have a prediction interval with valid coverage, it means that if I give you a model and a point prediction, you can turn this point prediction into a range that contains a true label 95% of the time. And that's really wonderful, because it gives you sort of a measure of how well you know the possible range of outcomes. If that prediction interval is narrow, you sort of know a lot about the outcome, and if it's wide, you don't know much. Okay, so that's conformal prediction, and it's very tempting to kind of deal with the uncertainty of AI predictions using conformal for my drug discovery problem. But we'll see that, unfortunately, there's a problem with that. So, here is what you might want to do naively. You'd say, Emmanuel, now that I know how to construct a prediction interval, you give me a threshold, and for the simplicity of this presentation, let's assume this threshold is the same for all drugs. It doesn't have to be. And for each drug, test drug, I'm going to construct a valid prediction interval for its potential label. And so you see, I have one for the first one for the second one, and one for the last one. And what's magical about conformal prediction, as I'm sure those of you who in the room who have studied it, it's valid on certain conjugations. These intervals have 95% chance of containing their true label, and it doesn't make any modeling assumption. So that's great. So we can deal with uncertainty, or can we? So it might be tempting to say, oh, okay, here are two drugs, and look, Emmanuel, my prediction intervals, they're kind of narrow and they're above your threshold. So I'm fairly confident that when we're going to go in the lab and test these drugs, we're going to find something that we like. Okay. And the problem, and that's the naive way of thinking. And the problem is, if you do something like this, chances are that you're not going to be very happy. And the problem is that when you do this selection, there is what in statistics we call a selection bias. There's a selection effect. Those molecules for which your prediction is high might be not at all like the other one. The problem with conformal prediction, it gives you validity only marginally, not over a very carefully selected set of molecules. And so when we apply this in real life, and you'll see a real example at the end, which we had a bit of back and forth with Genentech, I'll try to explain that. When you apply conformal prediction, well, it's really a wonderful theory. The theory works so well. You know, marginally, you have marginal miscoverage of alpha. You want a miscoverage of 10%, you get exactly 10% marginally. You want 20%, you get 20%. You want 30%. But what is the orange curve? The orange curve is what you care about. Is now let me run 1 million tests, and let me look at the interesting ones. Do the labels fall in the predicted range? And the answer is absolutely not. Your error rate is over there. You expect a 1% error rate, you get 30%. You expect a 10% error rate, you get 90%. Most of your experiments end up in failure. And this is a selection effect. And I'm sure a lot of you know about this. This is a problem that we have when we have the reproducibility of science. And so you cannot apply conformal prediction out of the box. You're going to have to deal with this selection effect. Okay. So what we're going to do is we're going to try to first show how we could do reliable selection when we have no shifts, and then we'll take care of the shifts in a minute. So what we're going to do is, and this is my most mathy slide, we're going to calculate what you can think of, if you've studied conformal prediction, of a conformity score. But that conformity score will have to be monotone in Y. And I'm not going to be too too general in this presentation. I'll just give you examples. So we're going to look at a conformity score, which is the difference between the affinity and your predicted affinity. It's just a residual, except it's not signed. So for the training drugs, I can compute this conformity score, and for the test drug, I cannot, because I don't know their Y's. So I'm going to plug your threshold instead. So I have a conformity score that I can calculate for the training drug, and for the test drug, I'm going to replace the true value of Y with C. And now I have my test drug over there, I have my training drug over there, and now I'm going to call something, I'm going to calculate something that looks like a p-value. And the p-value is calculating the number of training drugs that have a conformity score smaller than the conformity score that I would receive if I had plugged the threshold. So now what does this mean? It means that I'm going to, suppose that for those of you who have studied conformal prediction, suppose that if I had plugged yn plus j here, then the vi's and the vn plus j would be under no distribution shift exchangeable. And so the rank would be sort of uniform. So we are counting the number of drugs that have a conformity score which is below these adjusted conformity scores. And it turns out that if I do not have distribution shift, something really wonderful happens, which is that this is really a true measure of reliability. That is, if indeed this drug is not interesting, that is, it's random, its Y is below my threshold, then this measure that we defined is less than alpha with probability at most alpha. So what it says is that if you're not interesting and you see a very small value of p, p cannot be below 0.05 with chance more than 0.05. So what we're going to do then is we're going to select those drugs that have small pj's. And so for you, the takeaway of this thing is, why do we want a small pj? We want to take a small pj because if pj is small, it means that this has a low rank. So this is small. So Vn plus j is small. And therefore, Cn plus j minus mu hat is small. And therefore, if your prediction is any good, your prediction algorithm is any good, your forecast algorithm is any good, it means that y hat is very small, if mu hat is a proxy for y. Okay, so it's likely to be large and above threshold, and so we're going to do that. Okay. So then what we have is we're going to bring two fields together. We have conformal prediction, and then we're going to take ideas from statistics now. We're going to compute these calibrated metrics, these PJs, and then now we need to select. And we're going to select by a method called the Benjamini-Hochberg procedure, even though there is no Gaussianity, no parameter. These random variable we define are all dependent because they all depend on the training set. But we're going to ignore all of that, and we're going to select by Benjamini-Hochberg procedure. I'm not going to introduce the Benjamini-Hochberg procedure. It's a very, very simple procedure that will look at this p-value and select those molecules whose p-values are below threshold, and the threshold is chosen adaptively. And it's a very, very simple procedure. Now, this is Yoav is a friend of mine. His work has influenced statistics enormously over the last 3 decades. For those of you who do not know about the false discovery rate, it's one of the most important ideas that came out of statistics in the last half century. So it's a very simple procedure, and lo and behold, when you apply this procedure, something really unexpected comes out, which I did not expect. So this is work with my graduate student, Ying Jin. When you apply this procedure, the fraction or the expected fraction of false discoveries that you're going to make, or the expected fraction of the budget you're going to waste, is below what you want. So you give me alpha, it can be 20%, 30%, 10%, 5%. You tell me your risk aversion, and I'm going to apply this procedure. I made no modeling assumptions of any kind, and at the end of the day, we're going to send for testing those that have been selected by the Benjamini-Hochberg procedure, And I can guarantee that the selection will be, the fraction of wasted experiment on average will be less than your threshold. You want 50, you'll get 50. And to me, it is a bit surprising to see how well it works in real life. This is real data now. And so as I mentioned, this is work with Genentech. This is retrospective. I'm going to show you prospective studies in a minute. But this is real data. We were asked to select gene perturbations with high T-cell proliferation. You know, there's a very fancy algorithm that is trying to predict those perturbations. And we use as covariates the learned representations in a hidden layer of neural nets. The prediction algorithm is very complicated. I don't pretend to understand it, and I don't think nobody does. So we want to find genes that lead to high T-cell proliferation. And to me, as a forecaster, this plot makes me very happy. The red line is what we achieve. So this is a target that the lab manager gives us. They want 20%, a hit rate of 80%, so 20% error, 25, 50, etc. And you see what we select drugs that are exactly falling onto that line. Like we have no idea ahead of time which of these drugs will work and which will not, and yet I can give you a perfect prediction of the fraction of error that you will see. If you do not apply this method, if you apply conformal prediction without taking into account the selection effect, then you get this blue curve. And of course, this is a problem we saw before, which is that the error rate shoots up. You think you're going to get 1% error, you get 50. And so before you know it, you lost all of your budget. Okay, now we're going to need to deal with distribution shift. And that part, maybe I'll go a little bit quicker. To deal with distribution shift, these two classes of drugs are not the same. So we're going to use an idea that comes from the field of causal inference. And to do distribution shift, we're going to look at the features that we learn from the data. So this could be like embeddings of these molecules that these neural nets have found. And we're going to make sure that if we call this feature phi, then we're going to find weights. We're going to upweight some training molecule and downweight others so that the moments of the features match. And so we're going to try to upweight and downweight molecules in the training set in such a way that this weighting is as close to uniform as possible. This is what this does. And yet, when I look at the features, the weighted average of my features is sort of the same across training and testing. Once I have this weight, I'm going to reweight these comparisons that I'm making by some molecules will be upweighted, some will be downweighted, and so I'm going to compute a new p-value that will upweight some points in a training sample, downweight others. There's a selection procedure that comes after that, which is more complicated than what we've seen. And if you do things correctly, you will control the FDR as well. Okay, so this is good because it means that we can deal with distribution shift. And many of their problems have huge distribution shifts. So here we use a transformer trained on proteins. And we try to select proteins with high stability. And I cannot tell you how happy it is to find of course, it's not perfect because I did not probably capture the distribution shift exactly, but it's very close to a 45-degree line, and this is what you get if you do not apply this technology. This is another one. We select combination of genes. There's enormous distribution shift in this data set. So here we use a Gears graph neural network, and here we do get a perfect straight line. And so I'm really, I don't know, it's very bizarre to be excited about a straight line. But I'm excited by this straight line because to me, it's kind of a very important forecast problem. If I test these molecules, how many errors will I make? And somehow, we estimate it perfectly. All right. Now, let me go a bit in prospective mode. So then after we did that, like Genentech was convinced that, well, we hold something interesting, and so we're going to use that to actually find new drugs. And so they did. We started with a library of 460,000 molecules. Of course, they're not interested in finding molecules that look like things that they already know about, so they did a lot of filtering and diversity filtering, and we were down to 15,000 molecules. And then we applied the methods, and we wanted to find an antibiotics, and Genentech, in this case, came to us and said, here are the 100 guys that we'd like to screen. What do you think? And we looked at them, we applied all the techniques you've seen, and we said the estimated error is going to be between 70 and 95. We estimate the false discovery rate to be 80.5. So we expect that there will be 19 hits, but maybe as low as 6 or 5 and no more than 30. They were very puzzled by this, because for them, they would be all hits. So we said, no, you'll see 19 hits, perhaps fewer. Okay? And of course, they were puzzled. They'll say, okay, so you're telling us we'll use 80% of our experiments? Yeah, I think that's kind of what you'll see, perhaps even more. And so they actually went and did this test, and they got 91 errors, only 9 hits, when they were expecting 0 error. And they were expecting 0 error because they were using conformal. And conformal ignores 2 things. It ignores the selection effect, it ignores the distribution shift. And so for them, they would all be hits, but they were none. This is our method. This is the method I showed you. We predicted a false discovery proportion of 80+%, so hit rate below 20%, and they got 9%. And unweighted, it's if you take care of selection but not of distribution shift. So you're also in the dark. And here are the 9 molecules that at the end of the day we found and now are being really thoroughly tested for drug development. Okay, so I took a little bit of time to explain this. We can do a lot of different things, but maybe now it's time to move on and tell you about other things. So the other things will be shorter. They're just going to be short vignettes of other problems you might find interesting. This maybe I'll skip, but what we've done is we've developed a system that, of course, when you ask ChatGPT a question, ChatGPT is very happy to oblige. And, I could ask ChatGPT, how often is a shingles vaccine required? So there's a real prompt and a real answer. And, it says a shingles vaccine is typically recommended for adults aged 50 and older, blah, blah, blah. And so what we try to do here, and it's again has a flavor of conformal prediction, but it's far more sophisticated than conformal prediction, is it possible to take this text, filter out some claims that do not seem right? All right, so for example, in this case, it might be removing this claim. It is currently recommended that individuals receive a shingles vaccine once in their lifetime. Remove claims that look dubious, and then give you something to read with an estimated probability of authenticity, that it's actually correct. And of course, you don't want to remove too many things, so you want to kind of guarantee factuality. And so, you could try to do something like this, and we have created a system that takes an output of ChatGPT, parse the claims, keep some, delete some, then give you the claims that we think you should read, and it's going to give you a probability that what you actually read is correct. And so, okay, I'm going to skip the details, but it's gonna it's going to remove claims, and maybe I'll skip that because I'm out of time. But again, Emmanuel excited about 45-degree lines. We created a system, it's going to parse claims, remove claims, etc. And no matter the medical question, the type of medical question you ask, it's going to give you, I think it's correct with probability 75%. And what does it mean? What you see is correct or it's not correct. There's no randomness here. What I mean is whenever I announce, and this is really a forecasting thing now, whenever I announce 75%, empirically I want to see 75%. When I announce 60, I want to see 60. When I announce 30, I want to see 30. And that's what we see here. Right? So what's very nice about this is that you can try to kind of build engines around these LLMs so that you have a sense of what they tell you, what chance does it have to be correct. Of course, there is no probability, but it means that historically, if I were to forecast, and I say 65% of the time, what I'm showing you is correct. Okay. All right, so I want to kind of move really now into LLM questions. Still, my next vignette has to do with forecasts. And it's kind of an interesting problem when you think about it. And it's really about your field, this one. But it's a very strange thing, and you're going to tell me what you think of it. Okay, I'm going to skip the thing. What you should know is that Frontier's lab spend enormous amount of time collecting labels and verifying answers. They pay mathematicians a lot of money to verify proofs, to come up with proofs, to label stuff. And, there are companies whose job it is to verify things, and people spend billions of dollars doing it. And so the question is, can we automate part of this using LLM as judges? And that's what I want to talk about. So is it possible to guess a label without spending too much money? And so I'm going to pose a problem to you, and you're going to tell me what you think of it. I asked ChatGPT a question, or I think in this case we work with Google, so this would be Gemini. So I think that's actually a real thing you're looking on the screen. So you ask Gemini a question, and you can ask the same question many different ways, or you can even ask in the same way. You know about LLMs, these things are stochastic, you're going to get different answers each time. So Gemini might give you 50 or 100 different answers to the same question. Sometimes they're the same, sometimes they're not. And the question is, so these answers will be the rows of a matrix, and then the columns are LLM as judges. And what you ask your judge is to say, does it look right to you, this answer? And so the columns are my judges. And as you can imagine, your task is very simple. Which answer is correct? Which of these 100 answers that Gemini give me is the correct one? And have the views of LLM as judges. So how can I aggregate these LLMs to come up with a best answer? So we are the World Cup is going on right now. So here's a different version of this problem. You have 20 games that are going to be played in the next 2 weeks or whatever, right? I have 50 forecasters. They all tell me France will win, Netherlands will lose, etc., etc. So they are over there, right? How do you ensemble these forecasters to get a better forecast when you have no ground truth? I have no idea how reliable is a forecaster. None. So it's different from what you've seen. Unless you've seen something like this before, there is no supervision. I have no idea who is a good forecaster, who is not a good forecaster. None of that applies. The question is very, very simple. You make forecasts about the World Cup. I have 50 forecasters. Is there a way to ensemble them? And these games are going to be played once, not that we're going to repeat the World Cup every year, right? Every day. They're going to be only played once. These games are going to happen. There's only one answer here that works. How can I ensemble them and get a better forecast? Because that's a question. And no supervision of any kind. Of course, we could talk about the stock market. Forecasters, they say this stock will go up, down. How do you ensemble this forecast to get something half decent? All right, so that's a problem. And, and here is something very pretty. Okay, so if the verifiers, that is the forecasters, are conditioned, so let's assume that we need to predict whether a team will win or lose, or whether an answer is correct or not. And suppose that my forecaster, just for the sake of this presentation, just tell me, I think it's correct or I think it's incorrect. Let's say that they have this form. So forecaster 1 will say, no, this is wrong, it's -1. Forecaster 2 will say it's wrong, it's -1, etc. And let's assume that condition on the status of the claim, of the answer, so y is 1 means that the answer is correct, y is -1 means that it's not correct. Suppose that condition on the status, these forecasters are conditionally independent. That is, our errors condition on the we are decorrelated. Okay? Then if that's the case, there is something that is very nice about this. If I start to compute the correlation matrix or the covariance matrix of this forecast, so I'm calculating the covariance between forecaster 1 and 2, 2 and 3, 3 and 4, etc., I'm going to look at moments of this data matrix. And if I look at moments of this data matrix, then something kind of very beautiful happens. The covariance between forecaster I and J is equal to, it's a product of 3 terms when I is not J. 1 minus B squared. B is class imbalance. It's the fraction of times the answer is correct minus it's wrong. Pi I is the accuracy of forecaster I, and pi j is the accuracy of forecaster j. And accuracy is basically defined as you think it is. It's the average of psi plus eta, where psi is your sensitivity and eta is your specificity. Okay, so what's remarkable about this is if I start to look at the covariance matrix of this forecast, off diagonal I see a rank 1 structure, and the rank 1 component is telling me about your accuracy. Okay, so this is very, very cool, because by looking at the first principal component of this covariance matrix with the diagonal removed, I'm going to learn about your accuracy as a forecaster. So this is what we're going to do. In real life, what we're going to do is we're going to transform the verifier scores to make them approximately conditionally independent. And that we're going to do by calculating higher moments. So there's a bit of technology in there. So we're going to try to make this assumption hold as best as we can. And then we're going to compute the first principal component of a covariance matrix. This is going to tell me about your accuracy as a forecaster. And last, now that I know which forecasters are accurate and which one are not, I'm going to take a weighted average of their forecast. But weighted, you're going to get a higher weight if you somehow, I've detected that you're a better forecaster. So this is a simple methodology that we're going to apply. And so this is being presented at ICML as we speak. And that improves a lot performance. So you can get and correct labels and find the right answers by a significant, it's going to lift performance quite a bit. So we have benchmarks in LLM. We have GPQA Diamond. This is a science benchmark. We have MMLU Pro. This is a tough benchmark, IMO. You have to solve a Math Olympiad problem. Okay, International Math Olympiad problems. And so what you're looking at here is you're looking at best of n selection over the baseline on 3 benchmarks. So what is a baseline? Is like the success rate of Gemini when I ask Gemini once, what do you think is the correct answer? And so what we see is we see a 22% improvement over PASSAT 1, right? So PASSAT 1 is the best improvement, is a naive answer. For MMLU Pro, the lift is 21.5, and for the IMO, the lift is 10.5%. And so this is kind of remarkable. So this is a method you've seen in deep red. In blue, what is that? It's a method that was developed at Stanford by my colleagues, but that uses actually labeled data, and I don't know where they get labeled data. Like, we make forecasts. It's not a supervised problem. And yet, what's kind of, even if you have labeled data to learn who are the good forecasters and who are not the good forecasters, the red method seems to at least be on par, if not do better. So, and so this was exciting because it means that in a totally unsupervised fashion, you can actually pick a better forecast. So you can ensemble this forecast even though you have no idea about what the ground truth label is. And Pierre tells me that I'm at time, so I should wrap up. I wanted to talk to you about pre-training, but that would be for a different... so this has nothing to do with forecasting. If you like, during Q&A, we can talk about this. But basically, you're familiar with scaling laws, and we have more compute, the data set gets larger, we build models with more parameters and so on. And so things are going well because it seems like there's plenty of data to go by and keep on improving models. But that is coming to an end. And that end is that if you look at what the Frontiers Lab have done, is that they pretty much have exhausted all human-created data. So what do we do next if we want scaling to continue? Well, if what we want to do next is, if we don't have human data, we're going to have to use, I guess, synthetic data. And the question is, what kind of synthetic data should we create for it to have any value? And that was this last part of the talk, but I'm at time, so I think I should stop here and leave you with my wonderful collaborators that you see here. Of course, I don't do this work in isolation. I do it with remarkable students, and you see some of them here. Thank you very much.
Thanks very much, Emmanuel. It was a very nice presentation, very inspiring. Are there some burning questions now? Yeah. Maybe I give you.
So thank you very much for the presentation. I have one question regarding the last topic you spoke about. So when thinking about like a meeting of LLMs trying to decide what's the outcome of some question and trying to average them, wouldn't it be better or maybe one possibility also to try to know the LLM first, to try to know how, I mean, as you would do with a person, right? If you wanted a person to generate a good outcome, when you ask a question, you try to know the person and know how this person will respond to some question or some other question, and then when you know it, then you can like rate this or weight the answer, right?
You might, but that now you become supervised, and that is a possibility. So you say, I should not be unsupervised, I should be supervised. And when we talk to our partners, they say, yeah, but being supervised costs a lot of money. And things change all the time also. These LLMs that come online, they change all the time. And so, yeah, I mean, I agree. I mean, you know, the more data you have about my forecasters, the better. But to us, it seemed like interesting to say, here are my forecasts. I have no historical data for these people. What is the best answer? Now, could you spend a lot of money trying to assess their accuracy? You could. But then, you're going to have another problem. It says, I look at this forecast, and you looked at whether this guy was good at recognizing good math proofs, right? And now this question is about the universe. Like, what good does it do?
I have another question here.
Good morning. Thank you very much for the talk. I was wondering also on Fuse, does the accuracy vary with the number of judges that you have? So if there are fewer LLMs that you're judging, does the accuracy of aggregating them change based on if you had more?
Yeah, so if you have a bit more, you're gonna start to benefit from the wisdom of the crowd. If you have a suitable assumption, so having more judges that are a bit better than random and conditionally independent is helpful, absolutely. Now, maybe I should say one thing, which is that, maybe not.
Next question.
I mean, one thing is like,
Go for it.
this sounds surprising that we can do this stuff, right? You have no ground truth. I mean, I think you really need to think about this in terms of the World Cup. I have to predict 20 games, and I have 30 forecasters, and for each game, the forecaster will tell me which team loses and wins. And then the thing is, how can I use this data to get a super forecaster without the games have not been played, and I have no idea about the historical accuracy of any of these forecasters?
Okay. A quick last comment. I see people are going to start going to the next session.
So in your first experiment with the drug identification, you are looking for known affinities where you have already identified a mechanism of action for that class of medications. Mm-hmm. So we're limiting the possibility by only doing drug discovery that way for diseases and mechanisms of action that we know, and not allowing for creativity and unknown patterns.
That's true. So there is a score I need to predict. It's your affinity for target. And so, for example, I remember we worked on HIV, and we have to block a site on the so that the reverse transcriptase cannot be expressed. And there's a certain site on which we have to bind to make it happen. That is a target. We don't know all the sites. I agree. We don't know all the sites. So this is...
They are boundary conditions, yeah. All right, but I think we need to close to make sure everybody has time to get to the next session. Once again, Emmanuel, thank you so much for sharing your ideas, your works and perspectives. And thank you to all for attending. Let's move on with the day. There are lots of other exciting sessions. See you around. Thank you.
Thank you so much.